Okay, let's try this again. Maybe it'll work better.
It's like a unrestricted free agent. I just said, you know what? I'll give him
All right, so what we're going over today, we are going to continue with the rock lecture. I believe that I found a pretty good way to do a lab for y'all and for the people online. I'm just going to have to record some things on the iPad, but I think I found some better material than I had last year. The rock labs aren't too bad, and you'll see the rock lab chart in a second in the PowerPoint. The minerals are very hard because there's thousands of minerals, and it's hard to find a good, informative kind of lab procedure where you're not just kind of being overloaded with minerals, and you're like, "What is this? What like is it this one?" And I'm like, "No, that's not. That's not in the lab." So I think I got some things done yesterday. I worked on it for a couple hours. And it should be better. And I think it's stuff that if I do the video right, I should be able to send the online students some paperwork, and they should be able to answer the questions. And so I think I'm going to have the questions be answerable in Canvas. That way you don't have to like write out anything on a lab paper or anything, and it's all still online. I might print out some papers for y'all to use in the lab, but you should have to take your Chromebook around and answer the questions there. That being said, I did get the homeworks up this morning. I didn't last night because I was watching the game. But they are up now for chapter 1 and chapter 2. I might change the due dates on those. Right now, they're due Wednesday of next week, which is a little over a week from now. There's not a lot of questions. I think the first one is 8 questions for chapter 1, and the second one is maybe like 12 to 14 questions. I don't think it's a lot for chapter 2, so they shouldn't be too bad. That being said, if we aren't taking the test at that point in time, then it will kind of be pushed back because I want y'all to have enough time to get them done and to study for the test. And I don't want to take the test too early. So I'm thinking we'll go ahead and finish this chapter lecture, which we should be able to get done with Wednesday, maybe Thursday. I didn't get as far as I'd hoped today, so we might get done Thursday. Friday is a half day, so we're not going to have a lot of time to do anything. I might show you all some videos Friday. I actually found some nice videos of petrology slides on YouTube, so we might look through some of those because petrology microscopes are very expensive, and getting petrology slides can kind of be tough too. So we're not going to be able to actually look at the slides, which would be really great and fun. So YouTube videos might be a good alternative. So we might do that Friday, and then ideally, if we don't do the lab on Thursday, we'll do both the labs next week. Early next week, we'll try to get both the labs in, the mineral lab and the rock lab for chapter 1 and chapter 2. And then after that, maybe we'll have one day where y'all can kind of catch up on your homework and think about the labs, and then we'll take the test. So as we get closer to that, I'll solidify the test date. But probably late next week, we will take the test for both of these, and the homeworks will be due. So make sure you take a look at them, and if you have any questions, let me know, but they'll be the same kind of format as the last homeworks. So this is where we left off yesterday, and it appears my computer is recording. Y'all ever watch any YouTubers that are always like, did I press record in the middle, and they don't edit it out? I think it's funny. But I did record last class, and it just didn't save it. I don't know what's going on, and they won't let us put any attendance in, but that's not for y'all. Sometimes I just gotta like complain to myself. But the Stars won last night, and they're going to the Stanley Cup Finals, and so today's a great day. We might get destroyed by Tampa Bay, but then again, we're supposed to lose to all of these teams, and this team just keeps winning. So maybe Stanley Cup's in our future this year. You never know. I certainly won't feel bad for Tampa Bay because they have a lot of good players, and will probably be back next year. Where this team, like, I was watching a guy on YouTube because I watch a lot of YouTube videos, and he's like, "It's just crazy that this is the team that's going to win because the Stars have had so many better teams than this, like with better players and have had better coaches, and like this apparently is the year where they're just gonna get it done." So if you're somewhat interested in hockey, check out one of the games later this week. Might be as early as Thursday, depending on what happens tonight. Uh, Back when they won the cup in '99, there's a bunch of people that started playing hockey then. Some of them are in the NHL right now. Uh, I started playing roller hockey. As exciting as that sounds, but yeah, went to the roller rink, played in the hockey league, and then as an adult, I learned how to ice skate, which is not an easy thing to do, and played ice hockey at the mall. Uh, and I know some of the athletics guys will know this. It's nothing worse than locker room stink. Like it's just terrible. And hockey pads, like these guys will play hockey and they'll take their pads and literally right after a game, soaked in sweat, they'll stuff them in their bag and throw it in the back of their trunk. And it'll stay in the back of their trunk until the next week. And they pull it out and there's just like fumes wafting off them as they're skating around the ice. And yeah, you should just have to like try not to throw up. But hockey's fun to watch, fun to play. Also expensive to play. So I don't know why I'm rambling about this because I'm just really happy from last night. I was like running around my living room, screaming and scaring my cats. And I woke my wife up and she went to sleep because she's like, I can't watch this. She's like, I don't know how I'm going to watch the finals. Like, I'm just like crazy nervous. Yeah, it was awesome. So back to geology. The people watching this at home are going, oh my God, is he going to get to the point?
Well, they can skip through the video.
Yeah, they can fast forward. You can fast forward. You have that option. The people in class don't have that option. They just have to listen to me. So this is actually a pretty good picture to show you the 5 different textures of igneous rock. So you have a volcano here. You have some plutons underground, some of which have cooled a little bit. And this image, I want you to kind of think about when we talk about Bowen's reaction series, probably tomorrow. I think that's where I'm going to leave off today. But this kind of image of them cooling from the outside towards the inside. So they start off fully molten, and then as they cool, the inside is probably the last thing to cool. So we're going to start here with glassy texture. These 3 are all going to be volcanic rocks. So they came out of the surface. They were formed from lava. The glassy one we're starting off with forms the fastest. Almost instantaneous cooling. There's no chance for any minerals to grow or really separate from each other. And so it's just a mix of ions and atoms. You can't really determine what minerals are in there. It's hard to even call them minerals. You kind of just have to look at the chemical composition to guess what kind of minerals there would be. If you were going to call it minerals, it's probably a lot of quartz. It has a similar hardness to quartz. It kind of acts like quartz in a way. But yes, we will talk about obsidian in a little bit. So there's your glassy texture, volcanic rock. Here's your vesicular texture. This is one that's going to be cooled as it's exposed to air or water. And so the air and the water is very volatile to molten rocks. It causes a lot of bubble and a lot of spattering. And those bubbles get solidified in the rock. And so you have this nice rock that has a bunch of holes. And this is pumice, exactly like you use pumice to kind of scrape your heels in the shower. It's a useful rock in that way. Over here, we have our other lava rock or extrusive rock. And so this is just your plain fine-grained texture. This is a rock that came from lava on the surface, but didn't really cool super, super fast. Wasn't really exposed to water or air. Probably cooled underneath a layer of other lava. And your cooling time for this, you're talking like years to like a decade maybe. So not like super, super fast, but not as like quick as you would think still. This lava does take a long time. When a volcano like Hawaii erupts, you can't just go like a week later and walk on the lava that was just lava like a week earlier. It's still very hot and takes a long time for that that energy to dissipate. If you come down here, you have your only coarse grain rock. This one is a granite. This cooled underneath. And so well underneath the surface, very insulated. This is going to take thousands of years, if not hundreds of thousands of years, to cool down, sometimes even longer. The minerals inside had plenty of time to grow big crystals, so you can see them with your eye without using a magnifying glass or a microscope. And then your last one, porphyritic. This one's going to have both. So this would have been a rock that started off in one of these plutons, started to cool down, it started to grow some minerals here, and then ultimately it was erupted in the volcano, came up to the surface, and the rest of it cooled very quickly. And so you have some large grains like you would see in the coarse grain rock, and then in between these large grains, you have a fine grain texture like you would see in the fine grain rock. And so those are your 5 textures for igneous rocks, and we'll see these on the chart in a little bit. You have glassy, vesicular with the holes in it, you have fine grain and coarse grain, and then porphyritic has both fine and coarse grain. And so it kind of shows you where each of these would come from in a nice volcanic setting. So they're going to start by talking about silicate rocks and your dark silicates and your light silicates. Remember the silicon-oxygen tetrahedron that makes up a lot of rocks and minerals. Remember also that chart that showed that silicon and oxygen made up like 75% roughly of all the elements at the Earth's surface. And so a lot of your rocks are going to have this silicon and oxygen. It just depends on how much and what other minerals they have with them. And so for igneous rocks, you have a lot of aluminum, calcium, sodium, potassium, magnesium, and iron. And this makes up about 98% of most magmas. And we'll talk in Bowen's reaction series how you can kind of have all these constituents in 98% of your magmas, but it can create all these different rocks. And Bowen's reaction series really kind of explains how you get different rocks out of magmas that are pretty similar. So your dark silicates, the ones that we will see form your mafic rocks in a little bit, they're very rich in iron and magnesium. And so this iron and magnesium help keep them dark, and they're relatively low in silica content. They're always going to have some because those are your main constituents, but relative to the light ones, they're low. So those kind of rocks are olivines, pyroxenes, or these are the minerals. Olivines, pyroxenes, amphiboles, biotites. All of these are black. Olivines usually black, but it can be like a dark green color. And so these are your dark rocks. And when we say dark versus light, we really mean, is it like black or a dark gray versus literally almost any other color? So it can be red, it can be white, it can be like a light gray. Dark silicates, really, you got to be dark. And there's not a lot of color going on there other than maybe like a dark green. Light silicates contain greater amounts of potassium, sodium, calcium, and are rich in silica. And so this is just like a taste, but you can see how geology has these many different branches. And some people literally just focus on geochemistry. What is the chemistry in the rock? What are the elements? What kind of minerals are created? How do they interact in the magma? You could spend a lifetime studying just the chemistry of rocks and not really understand everything about it. And so geology does kind of take from all the different branches of the science. So for your light silicates, you have minerals like quartz, muscovite, which is the light version of biotite, and feldspars, which along with quartz are a main constituent of granite. Granite has your quartz, your feldspars, and your hornblende amphiboles. So feldspars are the most abundant. They're about 40% of igneous rocks. So you do find a lot of feldspars. So they just kind of hammer home, there's 2 ways you look at igneous rocks. There's texture, and then there's composition. What minerals are they made up of? So we already talked about the texture, fine grain, coarse grain, vesicular, glassy, and porphyritic. This is the chart that we're going to use in the lab. And this chart is actually really, really helpful. The only thing I don't like about it is they put the words on the rocks, but didn't make the words different colors than some of the rocks, so it's really hard to see. You'll probably have a better chance seeing it on your slides on your Chromebook. I will find one to print out for the lab that is very legible. But unlike minerals, which there's literally over 4,000 minerals, and for common labs, you might use a couple dozen. This is it for igneous rocks. This is all the possible igneous rocks you could ever have, all in one chart on one page. And really, for the most part, there's just like 6, 7, 8. There's about 8. And if you can figure out which of these 8 it is, with a possible porphyritic tag added to it, you're going to be good to go. Now, the hard part is there's always a gradient. Very rarely do you have rocks that fit neatly into one of these categories. Luckily, I've got a pretty good rock set back there, and so for the lab, I try to pick things that do fit squarely in these categories so you don't have too hard of a time. But just to show you how this chart works, your textures are over here. So everything in this top row is coarse grained. You should be able to see the individual mineral crystals with your eye without using a microscope or a magnifying glass. Just below that, you have fine grained. So these are going to be relatively homogeneous looking rocks. You're not going to be able to see a lot of different things going on. It's just going to kind of look like a rock. We'll skip over porphyritic. We'll talk about this in a second. Glassy is down here. Note that glassy kind of goes all the way across. They don't really worry about the composition up here for glassy. On this one, they just kind of have it under felsic. There's plenty of these that have obsidian just go all the way across, because your ability to really know what minerals are in it is severely limited. You can kind of do a chemistry analysis on it, but that takes a lot of work. So obsidian is pretty much just obsidian. If it has this glassy look and feel, it's going to be obsidian. That's the only thing. And then vesicular down here, if it has holes in it, if it's light colored, we call it pumice. If it's a nice dark colored one like black or dark brown, we have a different name for it called scoria. I don't even know if I have a scoria. For the most part, if it's got holes in it and you call it pumice, that's going to be acceptable for this class. So these are your 5 textures: coarse grained, fine grained, porphyritic, which has both coarse and fine, glassy, and then vesicular. Now, up here, we have our mineral composition. So we have felsic, intermediate, and mafic. Felsic is going to be the light colored stuff. And notice they don't use white. They use pink. Intermediate is going to be kind of in between your light stuff and your dark stuff. It's mostly going to be gray, and more like a light gray than like a dark gray. Mafic is going to be your dark stuff. It's going to be black to like a dark gray color, sometimes a little bit green, but mostly black or gray or dark gray. And then over here, they do have ultramafic. We probably won't see one of these. These are pretty rare. And note that they just have uncommon here. They don't even have a picture of that one. So that kind of shows you how rare they are, that you don't even have a picture to put on your chart for that. So this is it. For the most part, it's these 6 rocks. If you can figure out, is it coarse grained, is it fine grained, and is it light colored, intermediate, or is it dark colored? You basically trace that down, and it tells you the name of the rocks. So to go over the names a couple times so you kind of get used to the names. Coarse grained and light colored is going to be granite. So these are your light colored rocks. They have a lot of quartz and feldspar, and this formed underground, so the crystals had plenty of time to grow. Now there's an equivalent for this. This is your volcanic rock. This one's called rhyolite, Rhyolite. You can find a bunch of these up in Oklahoma. They're not there anymore. Oklahoma used to have volcanoes. And because it's in the middle of the continent, it's a lot of light-colored rocks like this. And so you can find a bunch of these pink rhyolites up in Oklahoma. And so that's a rock that's not too far away from here. Moving on to intermediate. These are going to be gray rocks, or like a healthy mix of gray and black. And before I move on, down here, they have a nice scale to show you how much dark minerals you should have. So like for felsic, you can have up to 25% of dark minerals. So it's not like 100% light minerals. You're going to have a smattering of dark things in there. For intermediate, it's about 25 to 45%, so still less than half dark, which is why I say it should be like a light gray, or almost like a TV static kind of look, the white and black kind of staticies. And then mafic you're going to have 45 to 85% dark. And so it's mostly going to be a dark rock. You're going to have a hard time finding little light specks in there, even if they do exist. So for intermediate, we have two names. You're not going to see these too often, but you'll probably see them in the lab. Diorite is the coarse grain one. Andesite is the fine grain one. And andesite is named after the Andes mountain range because you can find a lot of these rocks in the Andes. And then if you go over here to mafic, basalt is going to be the most common one. Gabbro is around. It is the coarse grain one. You can find them here and there. Basalt is the volcanic rock. This is what you're going to find all over Hawaii. These are more common because in general, these gabbros don't really make it to the surface. They do like exist. They happen. It's just not easy for us to find because usually they're under the ocean and under the ground under the ocean. Where your basaltic rocks come up in volcanoes, and so there's a lot more of them at the surface. They're a lot easier to locate and to study. Now, we've gone over these names. Porphyritic is a little bit weird in the naming. If you find a porphyritic rock and you know that it has both large grains and small grains, you can see it, you know that it's going to fit in this column, you still have to go and name it one of these. So you're going to figure out, is it lighter colored? Is it middle colored? Is it darker colored? And which one does it have more of? Does it have more small grains, or does it have more large grains? And you're going to name it that rock and put porphyritic in front of it. So like if I have a rock right here, I know it's kind of the light colored rock. It has more large grains than it has small grains. I'm going to call it a granite, but I'm going to call it a porphyritic granite. And so there is no like rock that is just porphyritic. You have to figure out if it didn't have both of them, which category would I put it in, and then add the word porphyritic in front of it. So there are no like unique names down here. It's just kind of an addition to the names of these top six. If it's glassy, it's obsidian. That's what it is. If you read a lot of books, you'll be familiar with the term obsidian. Anything really deep black and shiny has obsidian qualities, especially if someone or something has really black eyes. They have obsidian eyes. And then vesicular pumice, we're all pretty familiar with that term. So this is your chart. You're going to find the texture. You're going to find the mineral composition or the color, essentially, light gray or dark gray to black. And then you're going to trace these together and find the name. Is it andesite? Is it granite? Is it rhyolite? And that's pretty much going to be it. This should be a lot easier than the mineral lab, which we'll talk about later in the week. So we're going to start to talk about the different chemical composition stuff. For granite, we also call these rocks felsic rocks. So granite is the main rock in that category. The entire category we call granitic. We also call it felsic. And this word comes from feldspar and silica, the two major constituents. So it has a lot of feldspar and a lot of silica in it. It's mostly light colored. Like I said, you can have up to 25% dark material. They say most contain about 10% dark material. It is mostly silica, and so it's a less dense rock, and we'll talk about density when we get to the plate tectonics chapter. But this is a major constituent of the continental crust. Most of the rocks you see in mountain ranges and just in general along the continents fit into that granitic category, either granite or rhyolite. And when we get to Bowen's reaction series, we'll kind of explain why. There's a reason these are the most common rocks. It's not just because they have a bunch of silica, which, that's the most common elements in the Earth's crust. It's also the way that they form, and we'll see that in Bowen's reaction series. So here's a nice picture. That's Half Dome, and so I believe, I should have looked it up, but Half Dome's in Yosemite in California, if I'm right. Recently, somebody like this guy scaled Half Dome without any cords or backup or anything. Like if he fell, he would have died. That was pretty awesome. Was that last year or something? Did anybody see that? I don't know. It was nice. He was a very talented rock climber. So yeah, granite is your coarse grain rock. Let me show you the uplifted part. Let me go ahead and redraw this. So what they talk about when it's uplifted, you start off and your granite is just in like a pluton underneath, and it's got to solidify and cool completely underground for it to be a granite. At some point in time, it needs to be uplifted though. Sometimes you can have, just like enchanted rock yesterday, you can have erosion happen and it kind of gets exposed at the surface. But that's pretty rare to have a whole bunch of erosion. So usually what happens is plate tectonics. So you have a plate here and a plate there, and obviously this is very like rudimentary. They're going to collide, almost like a car crash. They're going to be pushed into each other. They're pretty much the same rocks. One's not more dense than the other, so nothing's going to get pushed underneath. And when they collide, you're going to get your mountain range built up. And so there's nowhere for them to go other than up. And so they're going to get pushed up, and your rock, which was previously under the surface, let's say there's a pluton here, and maybe like some sedimentary rocks up above it, some sediments. Your rock that was previously under the surface is now going to be pushed up into that mountain range, and it's going to be exposed. And so that is one of the major reasons we see a lot of this granite at the surface, is because we have uplift. So where you have your mountain ranges that aren't super volcanic, you're going to see a lot of granite because that's what's up there at the surface. I will say the half dome was probably part of one of these plutons. And the whole pluton got pushed up, and then at some point in time, half the thing like cracked off and fell away. And so you have this nice like dome shape that's been sliced in half, which gives you the name half dome. So moving on to rhyolite. Granite is the coarse grain one. Rhyolite is the volcanic rock. So it's extrusive, has all the same colors and minerals inside of it. It just cooled very rapidly at the Earth's surface. And like I said, you can probably find a lot of rhyolites in the Oklahoma area if you go to the right places. Obsidian, that's your dark glassy one. It's still going to have a high silica content, but it does have metallic ions in it, which make it look black. You can find light colored obsidian or red obsidian. There's all sorts of different types that kind of show up. But if you have like an arrowhead or a spear tip or something, that is made out of obsidian. And a little side note on this, because I learned this in anthropology. If you take an anthropology class in college, they might touch on this. There's a whole science that goes back and looks at how they make these arrowhead tips. And basically, it's made out of a giant piece, not giant, but a pretty large rock of obsidian. And if you think about it, if they're making their tools out of this, they don't have like metal tools. They don't have files. They really don't have anything harder than this kind of rock right here. And so it's very difficult to break this into this perfect shape. And so they would use another rock, and they'd literally just take a round piece of obsidian and smash it. And they'd smash it apart in a very techniqued way. And they do it the same time every time. And so now, as we're going back and excavating these villages that they lived in, you can always find the hut of the person who made the arrowheads because there's little pieces of obsidian just scattered everywhere. And somebody one day started to put them back together like a puzzle piece. So they will literally put all of them, they'll find all sorts of different ones, separate them into different categories, and put them back together into a complete stone the way that it was before that person started to break it apart, with only this missing out of the middle. And they kind of recreate, okay, which was the first piece to come off, which was the second. And they discovered that they had very complex and well thought out and passed down techniques that evolved over time. And by putting these together and figuring out what exact technique they're using to make this, you can kind of place them in this lineage of craftsmen who created these arrowheads. And so it sounds like a nightmare to me, like the worst puzzle ever. Because all the pieces are black and it's like 3D, and you never know really if you're doing it right. But there's a lot of information to be had from the scatterings that came from around the arrowhead for these different tribes. So that's pretty interesting. I remember learning that. So yeah, that's your obsidian. When you get to pumice, it has the holes in it. One of the things they mentioned is that it floats in water, and then they prove it with a picture. It's got a lot of holes in it, so it's really light. There's not a lot of heft to it. It's not very dense. and it's kind of been exposed to that air and water, and then it cools, and all the holes get trapped inside of it. So, yeah. Now, moving on to basalt. Basalt is going to be your dark rocks. Mafic is what we call these, along with the word basaltic. And mafic comes from your two main minerals, magnesium and then ferrum, which is the old school, probably Latin term for iron. And so mafic, magnesium, ferrum, or ferric, which is what I usually say. These are going to be your very dark rocks. They're going to be more dense, and we'll get to this when we get to plate tectonics and how oceanic rocks get pushed underneath continental rocks. There's not a lot of quartz in these. And in fact, usually there's no quartz. It's mostly your darker silicate materials and some metals, calcium-rich plagioclase. Remember that calcium, even though it doesn't seem like it, calcium is a metal. It exists on the metallic side of the periodic table. So this is a picture of basalt being formed. Remember, basalt, unlike granite is the coarse grain one. Basalt is the fine grain one. So this is going to be a volcanic rock. You'll find these often in Hawaii. That's pretty much the only thing that Hawaii has. Iceland, some upper layers of oceanic crust, and then volcanoes that are near the coast. Volcanoes that are in the center of a continent are more likely to be granitic or rhyolitic, like the Oklahoma ones. But if you get into like Oregon and Washington, the reason you get this basalt is because the oceanic crust is being pushed down underneath the continent. It melts and comes back up and feeds these volcanoes. And so things like Mount St. Helens and some of the other volcanoes there have basaltic magma or lava that comes out. There is a coarse grain rock called gabbro, which has the same dark constituents to it. It's just not commonly exposed. Like, we do have them. I probably have one back there that I'll show y'all. It's just not something you find a lot because generally it stays in this oceanic crust down underneath the surface. And there's not really a mountain building process that goes along with this that can push these rocks up, or we can find them super often. And then we get to the middle rocks. Andesite, like I said, which is named after the Andes, which have a lot of these. These are just kind of going to be a little bit of both worlds. They're going to have some quartz. They're going to have some dark colored minerals, a little bit of both. They're mostly going to be light gray, or that like mixture of black and white equally, depending on if it's coarse grain or fine grain. So the fine grain one is called andesite. The coarse grain one is called diorite. And then if you get to ultramafic, it is a main constituent. It does happen. It happens a lot. But you'll see in Bowen's reaction series why we rarely get them at the Earth's surface. And there's a reason for that. And we will go over that in detail tomorrow. But these are going to be really dark, a little bit of green, like if you have your olivine in there, but mostly just a very, very black rock. And you can kind of see it again over here. They show you this again for extra measure. So this we're going to leave off today. Real quick, I just want to kind of give you an idea of what Bowen's reaction series is, because we're going to spend a decent amount of time talking about it tomorrow. I love Bowen's reaction series, which is a very nerdy thing to say, but I really like it. I like learning about it. I like teaching about it. And basically the idea is when you have your Pluton, all the magma in this Pluton is essentially the same when you start off, right? It's all mixed up. But somehow, as it all cools down, it gets erupted, we get all of these different types of rocks that come out of it. There are different magmas depending on what's being melted, but usually you get a wide variety of rocks that come out of it. So how does that happen? When you have this magma melted, there are no minerals. It's all just like melted atoms, ions and atoms moving around. And one of the things you have to remember about the minerals, just like any other material, it's going to have a different freezing point. Now, this is really, really hot. It's like thousands of degrees. So remember when I say freezing point, it's the same thing as melting point. Water freezes at 32 degrees. It also melts at 32 degrees. And so when we say freezing point, it can be a very high melting point as well. You're just going the opposite way. You're cooling down and things aren't melting, they're solidifying. So when your magma or your pluton starts to cool down and things start to solidify, certain minerals are going to solidify before other ones. They have different melting points and different freezing points. And so certain things will start to come out in the magma. And each of these minerals takes out a certain amount of elements from them. And so as those first ones solidify, gravity is going to do to solid things what it does in a liquid, and it's going to pull your solid things down to the bottom. That's just how gravity works. Even if it's in thick magma, over thousands of years, these first little pieces fall down to the bottom and they start to pile up. But because they solidified first, they kind of take all those elements with it. And so once your first thing starts to solidify, the magma that's left over around them now has a different chemical composition. There's less of minerals left over, and there's a higher concentration of the minerals that are left. There's less minerals that were taken out. So if you're taking out your irons and your magnesiums, those are going to fall to the bottom. And what's left over has even less iron and magnesium and more of the stuff that was left over, like silica and oxygen. And so as your magma starts to cool down, it changes over time, and you get all sorts of different minerals happening. There's kind of like a hierarchy of layers, which is essentially what Bowen discovered and what the entire Bowen's reaction series is all about. So we'll spend a little bit of time talking about that tomorrow. What slide did we get to? We're at 30. So we may not finish tomorrow with the slides. We might have to finish up Thursday, which isn't a problem. That'll give you all more time to work on the homework and to study for the test next week. So that's where we're going to leave off today. I'm going to turn the lights on. Hopefully this video works and I can post it on Canvas. If it does, people at home dress up in your Hawaiian stuff and feel good at home on Hawaiian Day, even though you can't be here with us. So have a nice day, and I'll see you tomorrow.